You know, isn't it funny how sometimes the simplest questions, just a basic question about making a choice, can totally unlock these huge, complex, and honestly beautiful mathematical ideas? Well, today, we're going to follow that exact path. We're starting with something pretty familiar and ending up somewhere you might not expect. So let's follow this turtle's path and just see where this journey takes us. Okay, let's kick things off with a classic. Picture this. You've got 5 coins, and you toss them all up in the air. Now, the key thing here is that the order doesn't matter one bit. Getting heads on the first, second, and third coin is exactly the same as getting it on the first, third, and fifth. What we're really doing is just counting the unique groups of 3 heads. It's all about selection, not arrangement. And the math tool for this exact job? It's called a combination. It's all about counting groups when the order is irrelevant. It answers that classic question, how many ways can I choose, say, k items from a set of n items? For our coin problem, that's 5 choose 3. Now, I want you to hold on to that idea of choosing in your mind, because we are about to see it pop up in a place you would never, ever expect it. All right, so let's step away from coins and probability for a second. It's time to meet our guide for the rest of this little adventure, a small turtle with a pretty big challenge ahead of it. So here are the rules of the game. Our turtle is on a grid, starting way down at the bottom left. The goal? Get to the top right. But there are some crucial rules. It can only move 1 step at a time and only in 2 directions, right or up. That's it. No diagonal moves, no going backward. So the big question is, just how many unique paths can it actually take to get to its destination? Now, you could, I guess, try to trace every single path by hand, but as you're about to see, that would take you a very, very long time. The real secret, the elegant solution, lies in a clever little shift in how we look at the problem. And it's going to connect the turtle's journey right back to our coin flipping problem. Let's look at a simple little 2x2 grid to see what's going on. To get from the bottom left to the top right, no matter which path you take, you absolutely have to make 2 moves to the right and 2 moves up. Think about that for a second. Every single valid path is just a different arrangement of the exact same 4 moves, 2 rights and 2 ups. So here it is, the big aha moment. If the whole journey is, say, 2n steps long, all we really need to do is decide which of those steps are the right steps. I mean, once you've picked out the right steps, the up steps are already decided. They're just all the other ones. The problem of counting paths just completely transformed into a problem of choosing positions. And this table just makes it crystal clear. The coin problem was all about choosing 3 positions out of 5 to be heads. The turtle problem on an n by n grid, it's about choosing n positions out of a total of 2n steps to be right moves. They are, mathematically speaking, the exact same problem, just dressed up differently. And that right there is the real power of thinking this way. Okay, now that we've had this powerful insight, let's really put it to the test. We're going to see what happens as we make the grid bigger and bigger. This is where you really get a feel for just how quickly these choices start to explode. Let's start at the very beginning, a tiny little 1x1 grid. The whole trip is just 2 total steps. We need to choose which one of those 2 steps is a right move. 2 choose 1 gives us exactly 2 paths, right then up or up then right. Nice and simple. Now let's scale it up to that 2x2 grid we saw before. Now we've got 4 total steps, and we need to choose which 2 are going to be right moves. Well, 4 choose 2 gives us 6 paths. See? The number is already starting to climb pretty fast. Okay, now for a 3x3 grid. The journey is now 6 total steps long, and we need to choose 3 of them to be right moves. 6 choose 3, that gives us 20 distinct paths. Whoa. Notice that jump? We've more than tripled the possibilities just by adding 1 more row and 1 more column. How about a 4x4 grid? Now our turtle has to take 8 total steps. We're choosing 4 right moves out of those 8, and the number of paths just explodes to 70. You can start to see how trying to count these by hand would be, well, pretty much impossible at this point. And finally, let's do a 5x5 grid. We're looking at 10 total steps, and we need to choose 5 of them to be right moves. You ready for this? The number of possible paths for our little turtle is a staggering 252. I mean, that's just the beauty of it all, isn't it? This simple, elegant idea tames a problem that otherwise becomes completely impossibly complex. So we've seen how just reframing a problem, Turning a question about paths into one about choices gives us this incredibly elegant solution. But what happens when we make the turtle's journey just a little bit harder?
Today, we counted every single possible path from corner to corner. But what if we add one more rule to the game? The turtle is not allowed to cross above the main diagonal of the grid. Suddenly, a whole bunch of our 252 paths are now invalid. So, how many are left? Well, answering that question leads us to a really famous sequence in mathematics called the Catalan numbers. But that's a story for another time.